All right, so let's get started. So before we start, if you guys put your kind of questions on the chat box or you come in front of the desk to ask me questions, don't forget to email your questions to the TA. Okay, so you can get extra participation scores. So, okay. So this is our agenda today. Last week we talked about physical memory management. And this week we're going to talk about virtual memory management, including like patch table and like some virtual memory things that you need to know. And then if we have some time, we can talk about some advanced research topics. So before we start, let's first come through some Q&A. So the first question is about how does the patch allocator avoid memory fragmentation? So as you know, there are two kinds of fragmentations, external fragmentation and internal fragmentation. So for external fragmentation, for Linux kernel, they're using patch size to solve the external fragmentation. Because if you align the patch size to 4 kilobytes, like when you're doing the allocations, then the minimum size is patch size, then there are no external fragmentation in this case, okay? Because you always allocate 4 KB, okay? And then, but if you always allocate 4 KB, just like to allocate a page, then there might be internal fragmentation, right? Because like inner the patch, maybe the data cannot fill the 4 KB patch size. So in this way, like Linux use the step layer to manage the kernel data structure. So in terms of the data, actually, data structure is one kind of data that probably will not fit the 4 kilobyte because 4 kilobyte is too huge for data structure. So data structure, just like the things you already learned, just like text structure, or like last week we talked about the patch structure. So those data structure, they are usually several 10 of bytes. So it is way smaller than 4 kilobyte. So we need to say, like, if we have a step there, then we can reuse this data structure. We can group the data structure together. Okay, so this can, in some degree, solve the internal fragmentation, but I mean, it just kind of alleviate. For Linux system, it is hard to purely remove the internal fragmentation. Okay. So the second question is, why is it necessary to allocate specific patch frames to zone-DMA? So the reason is for older I/O device, like including network cards, sound cards, these controllers, they were designed to perform DMA within the first few megabytes of memory. Because for those older I/O devices, their DMA controller has limited support on addressing. For example, maybe they can only address in several kind of megabyte of area. So this is a reason in ancient time, Linux has this kind of design philosophy, just like they are going to reserve the first several few megabytes for DMA usage. Okay. So I think this is a very similar question, is because you know there's zone DMA, there's zone normal, and then zone high memory. So I put it here to make it together to answer. So for patch frames allocated to user process, they are all belong to the zone dash high memory portion. Okay. So usually people are saying there are low memory and high memory in the physical memory address space. So for the low memory, they are using static mapping, and their classification will be the zone dash normal. And for high memory, they're using dynamic mapping. So dynamic mapping means they're using patch table, right? Because patch table is not a fixed mapping. And static mapping, you can think about just like the virtual address to physical address is a 1-to-1 mapping. So you can think about physical address 1 plus 1 offset will becomes, virtual address plus 1 offset will becomes the physical address. That will be the static mapping, okay? And why is the kernel limited to mapping only 128 megabyte of high memory? So the reason is in a 32-bit Linux system, the kernel can only address 2 to the 32 virtual memory address, right? Because it is 32-bit. So in Linux system, they can only address 2 to 32, and 2 to 32 is around it's around 4 GB. But because for the user process and kernel, they share the same virtual address space, right? So in this case, kernel can only use the topmost 1 GB. Okay, so this is part of the reason, like because there are very limited resource for kernel, and inside this one GB, there are at 96 megabyte, they're using static mapping. That is, they're using this zone-normal. Okay, and usually the kernel code, the kernel function, in most of the case, they'll be stored in this at 96 megabyte area. So there is still 128 megabyte left in this 1 GB area, and those are being used for the dynamic mapping. So in some cases, maybe kernel need to get some like dynamic kind of parameters, or like to have some dynamic design layer, then 128 megabyte can be used in a more flexible way. So how does Linux alleviate race conditions when serving multiple interrupts? So last week, at the end of the interrupts slides, we are talking about the top halves and bottom halves. And splitting interrupt handlers into top halves and bottom halves is one of the policy to solve this kind of race condition if there are multiple interrupts, because the most critical things that need to be finished will be put into top halves. And for those that can be delayed, they can be put into bottom halves. So even both top halves and bottom halves, they are belonging to the interrupt handlers, but only the top halves needs to be finished at the time that the interrupt handler is called. Okay, so the rest of the bottom halves, they can be due in some time, like system is during the light loaded time. Okay, so this is about the way Linux used to alleviate the load when there are multiple interrupts here. Okay. So the same things, we'll also do a recall for the last week, like we talked about the physical memory, because there is some relationship between physical memory and virtual memory. So we'll first do some recalls. So the most important things for physical memory and virtual memory, they are patch. Like patch frame is for the physical address space, and patch is for virtual address space. So they are all in the size of 4 KB. Okay. So for patch frame, like you already know, like in the physical address space, if it is kind of the 4 GB or like whatever you want, depends on how many DRAM there are in your systems, then they will be allocated, they will be split into a lot of 4 KB chunks. For each chunk, it is called patch frame. Okay, so usually in the 32-bit systems, the first 1 GB that are used for the kernel address space, and the rest of them, they're used for the user address space. Okay, so you can think about the kernel code that are placed in the kernel address space, and the user code there be placed on the user address space. Okay, so when you're running a program and the program is going to call the memory allocation functions, and kernel will allocate a patch frame in the user address space, and then kernel will update the patch table. So this part will be explained later, how the patch table works. Okay, so we'll skip this part. So next we would focus more about the patch frame part. So although the processor's smallest addressable unit is a byte, current system using MMU typically deals in pages, so usually it's 4 KB. And we also show you the data structure for the patch frame. Like there are several kind of fields that are going to describe each patch frame. So this is the data structure that we are using in Linux kernel. And we also do some calculation to say, hey, actually for each field, maybe it is like 2 bits or 4 bits. So it depends on which type it is. So you can do some calculation. So like for this data structure for only one patch frame, there will be around 40 bytes. And then if you have a lot of patch frames, so there will be some overhead there for the systems. So we also talk about like when we are going to do the memory allocations, actually we not only focus on the patch frame part, we also need to consider some memory characteristics, right? Because different memory systems, they have different structure. So we talk about there's UMA structure and the NUMA structure. So UMA is there is a memory controller between all the CPUs. Okay, and then for NUMA structure is we move the memory controller inside the CPU. So each CPU they have their local memory and remote memory. Okay, so in this way, actually, CPU accessing local memory will be faster than accessing remote memory because the distance is longer for accessing the remote memory. Okay, so in terms of this structure, we need to consider the memory node. So the granularity when we are doing the memory allocation, we need to follow this node, zone, and patch frame. So for nodes, it's about when we are going to do the memory allocations, we are going to see, we're going to understand the structure of CPU and memory. And if the process run in this CPU and it is required for some request for some memory, the memory will be allocated from this DRAM if it is possible. So this DRAM has higher priority to be allocated to this CPU. And this is the nodes part. And zone parts, you already know, just like there are 3 different kind of zones, like zone dash, DMA, dash normal, and dash high memory. So different data, they need different kind of service. They're going to be placed in different zones. So under the zones, the smallest granularity will be patch frames. Okay. So, but as you already know, like even we do this kind of hierarchy, actually zone dash normal, there are 800 something megabyte there. And zone dash high memory, there are way more than several gigabyte. So it is quite huge. In this case, how to do the memory allocation? So in terms of Linux, like if we are going to do the memory allocation on the physical DRAM, there are 2 kind of way. One is for user space memory allocation. The other is for kernel space memory allocations. So no matter which one that we are focusing on, they use the same allocator. Low-level memory allocator is called a allocate dash pages. So if you are familiar with Linux, you are already heard, if you are familiar with Linux, you may hear the key term called the body systems. So body system is implemented in this layer. Okay. So between the kernel space memory allocator and user space memory allocator, there are also several allocation policies here. So for kernel base, actually, you can use the K-memory allocation to work with the slab there if you are going to allocate some place for data structure. Because data structure is usually smaller than 4 kilobyte. So in this case, it will be a better fit to pick the K-memory allocation, like the kernel memory allocation. Okay. And if you are going to allocate for a larger space, I mean larger than 4 kilobyte there, then vMemory allocation will be a better fit here. So for me, vMemory allocation, it can make sure the virtual address becomes continuous, but the physical doesn't need to be continuous. So this is for kernel part. And then for user part, like when you call the memory allocation, the C library here, actually there are 2 different ways to do the memory allocation. One is called BRK, the other is called the mmap. Okay, so no matter mmap or BRK, they're just trying to, they will call the allocate dash pages to get the physical memory from the DRAM. Okay. So body system, we also talk a little bit about it. Just the key concept behind body system is to make sure the allocation unit is aligned to the 2 to the order. Okay, so here is an example is if a process requested a 2 to the 2 block, but there is no free patches in order 2 and order 3. So order 2 means the blocks maintained in this order 2 layer is 2 to the 2, and order 3 is 2 to the 3. So they are all continuous. So what I mean continuous is if it is 2 to the 3, then it means like we have add 4 KB memory patches that are continuous in this layer. So in this example, if like you are going to if a process is going to request a 2 to the 2 and there is no in order 2 and order 3, then Linux will check for the order 4. So for order 4, maybe we'll get one piece of the memory, like 2 to the 4 blocks here, and we will split into the half. Okay, so when we split into the half, then we can reserve the 2 to the 3 in this order, the layer 3 here. and the rest of the 2 to the 3 can be sent to the next lower level to 2 to the 2. Okay, so because the process only needs 2 to the 2 blocks, so the half of the 2 to the half of the 2 to the 3 can be allocated to the 2 to the 2 the process, and the rest of it can be reserved for the data structure. So next time, if there's another process comes and it requests for the 2 to the 3, because we already have 2 to the 3 here, then the body system will directly allocate this part to the process. So this is the body system. Actually, the key concept is just about to always do the allocation aligned with the 2 to the 2. Okay, sorry, 2 to the order. Okay, so slab there. So when the data structure is no longer needed, it will be returned to the free list instead of deallocated. So, sorry. Okay, so what I mean for data structure is these kind of things. So this one is for text structure, just like it is going to describe the process, or like PCB you already know in the undergraduate class. And then this one is used for the kind of semaphore. And then this one is for like inode. This is for file. So actually different kind of data structure, they were in different size. So if we mix those of data structure together and then to put it into the patch, probably there will be internal fragmentation, because you can image like if there is text structure and a file, but file is quite large and they are placed together. But if the text structure, I mean, if some process they are free, I mean, if we terminate some process and they free up their text structure, and in this case, actually, this memory slots cannot be used to store any other like inode data structure, because inode is larger than text structure. So in this case, why not just split it? Why not just group those text structure together and put in one patch or like several patches? In this case, we can reuse the space to store the future like text structure. And the same things for like inode, there are the same things. Actually, those data structure, they cannot, usually they will not be more than like 4 kilobytes. Usually there are several 10 to 100 of bytes there only. So the key concept of slave there is just to group those same data structure together and then to locate on the same patch, or like on the same few pages. Okay, so actually the stuff that acts as a generic data structure caching there. Okay, so for data structure caching, it's just because like, sorry, okay, here. So caching is just about, come to think about if this is a patch, oh, sorry, if this is a slab and instead there are several patches. So those patches, they will only store text structure in this case. So if one of the text structure is free, then we will not really remove this area, because in the future, maybe there are some new process that are created, then they can directly reuse this text structure, because all the process, they have the same text structure. The only difference is the field. I mean, the value of the field will be different, but they all have like PID. They all have like those kind of fields. So we can directly reuse the space. Okay, so this is the idea behind like what we are saying, like this is a generic data structure caching there. So this example, I will not go through it. We already go through it last time. Okay. So actually, there are two common libraries to allocate kernel memory. One is the K memory allocation. The other is the V memory allocation. I think the key difference between them is K memory allocations is using the static mapping, and V memory allocation is using the dynamic mapping. Okay, so what does it mean for using static and dynamic mapping? So like here, so the figure on the right-hand side, there are two different address space. One is virtual address space, the other is physical address space. So for the virtual address space, the top 1 GB, usually it is for kernel. So for this 1 GB, actually you can see like there are from 3 GB to around 3.896 megabyte. There are, sorry, 3.896 GB there for the kernel core or data, and they are using the K memory allocation. And then for this high memory area, I would say like for this more than 3.896 gigabyte area, we are using vmemory allocation. So as I mentioned in the prior slide, like k-memory allocations, we're using a static mapping, and this is the dynamic mapping. So the thing is like this. If we're using the static mapping, then we should allocate a continuous physical address space here. So from 0 gigabyte to at 96 megabyte, they'll be continuous. And the address here and here, we can use this simple function to do the calculation, just like the physical address equals to virtual address plus some predefined offset. Okay, we just make the offset, and then this area can be directly checked directly. So it is super fast. You don't really need to check the patch table, right? You can just directly do the mapping, then you can know where the data is. Okay, so this is the static mapping part. But for the dynamic mapping, it doesn't really like this. Dynamic mapping, usually we use the patch table to do the translation. Okay, because you see like here is so huge. The area here is so huge, but here we only have like 128 megabyte here. So actually, there are also several other processes that will share this area. So in terms of the virtual memory, we need some translation there between them. Then the translation there is called a patch table. Okay, so actually this is how the difference between the static mapping and dynamic mapping. Okay, so I think this high memory is not that super important. So I think I will just skip this for the recall. Okay, so today let's talk about the virtual address space. So on Linux, each process is given a unique and flat 30 or 64-bit address space. So what do I mean for unique? Unique is process can have different data at the same address in their own address space. So process can also share address space like thread. So actually, for each process, they don't really need to care about some other process where the physical address they are using. They can just directly work on their virtual address. Okay, so this is in terms of the process point of view. In the process point of view, it doesn't really know how other process works like. And system, system means the Linux kernel. Linux kernel can help out dealing with this confliction. Okay. And flat means like the modern Linux system doesn't use the segmentation here. So just like if you have took the undergraduate operating system, you may see there is another kind of memory management. They're using segmentation. But in Linux here, we are not using segmentations. We're using a flat memory. Okay. So memory address is a particular value identifying a specific byte in a process address space. So come to think about, if you are using a 32-bit address space, then it means like you are able to address 2 to a 32 byte, right? Because in current system, in current CPU system, CPU are using the byte addressable. So usually memory we can address in a byte. So for each 32-bit like string, it is possible to directly address which byte it is. So in terms of using 32-bit system, the maximum will be the 4 gigabyte memory address space. So I think those are just like definition stuff. And I want to let you know, if you have a C program now, I think this is a very typical C program and it's quite simple. And how does this C program be placed on the memory? Because when we are going to run a C programming, we need to load on the memory, right? And CPU can fetch the memory and run a C program. Okay, but how? So coming to our virtual address space, okay. So for each virtual address space, they're only dedicated for a process. Okay, so when this program is running, then it becomes a process. Okay, so we use a 32-bit as an example. Like the top 1 gigabyte is the kernel, and the bottom 3 gigabyte is for the virtual address space. So kernel, just like you already know in the last class, there are some kernel code, those kind of things. And then how about for virtual address space? So first of all, there are text section. There are data section and there are BSS section. So text section, you can think about it's just like after you're doing the compiling, those kind of things, you'll get a binary, you'll get an executable file. So the binary and executable file will be placed in these text sections. Okay, so you can see the example here is the code. So the whole code, I mean, there's a simple string, and then if you go in the compiler, those kind of assembler, you can get a binary. And of course, the binary will not look like this. I mean, there will be a lot of assembly language there in the binary. So this is for text section. And then for data section, actually, there are two kind of data. And this is data sections, no matter it's data section or BSS section, they are all for the global variable. So global variable like here, like they are outside the function, like int global 1-x here. So there are two different kind of global variable, initialized or uninitialized. So for the initialized one, just like you give it some value for it, they'll be put into the data section. And uninitialized ones, they'll be placed in the BSS section. Okay, so actually, like you can think about data section like when you are compiling the code, actually, if you already put the value inside the code, actually it will take a little bit space of the executable file. Like, right, because like if you have this kind of global -y equals 10, you need to be compiled into your executable code. Then when the program is running, actually we need to find where it is, right? Okay, so the BSS section is about there is no initialization. And usually in the systems, I mean in the compiler phase or like in the executable phase, there will be doing some default initialization. So usually it will become 0, usually. Okay. And then there is a user stack part. Okay. So there's a user stack. User stack that are used for storing those parameters or functions things. So usually in the main function, there are several uninitialized parameters here, and they'll be put on the user stacks. Okay, so you can think about most of the data that relate to the function, they'll be put on the user stack, including the function pointer, they'll be put into the user stack. Okay, and also the heap. So heap, their users serve for the dynamic memory allocation. So kind of think about there is the memory allocation here, and we are going to have the 20 byte here. And the 20 byte memory allocation for this P will be put into this heap area for using. Okay. And the last one is the library. Actually, when you are writing this hashtag include standard IO library here for C code, when you are going to use a printf function, a scanf function, actually this library, it is called a shared library because all the C codes can share this like standard library, right? So this shared library will be mapped into this memory mapped area. Okay. So this is how when you have this kind of C code, then how will it be placed on the virtual address space? So I still need to emphasize again, this virtual address space only for a process. So each process has their own virtual address space. So if there is another process, another C code, then you can get another virtual address space. So this is the reason that I say when you are doing the programming, you don't really need to care about if there are other processes running in the systems, and you don't really need to care about where the data is located on the physical address. Okay, so because kernel will help to do this mapping, and kernel will help to solve the confliction if there is two virtual address point to the same physical address. Okay. So actually, not every address is legal. Intervals of legal address are called memory areas. And actually, we will have more examples for memory area later. So actually, there are several permissions for different memory areas. Then we'll talk about it later. So actually, when we are going to deal with this memory management things, like, for example, what is the size of the text section and what is the size of the heap? And because heap is for dynamic mapping, so maybe heap will grow and stack will also grow in these directions. So actually those kind of things, how to handle them. So we need another data structure. So actually this is called data structure. So this is a memory descriptor, and this is for the virtual memory. So if you still remember last week, we have the patch structure. The patch is for the patch frame. Okay. So this is a kernel data structure for managing the process address space. So you can see there are a lot of different kind of field here. So there is two very important things is there is a things called star mmap and mm-rb. So actually this star map and mm-rb actually even there are different data structure, there are different fields, but actually they are referencing the same content. Okay, so like this, they are saying about what is the size of this and what is the size of this. So actually, they store the same content. The difference is they're using different data structure. So the reason is there are two different ways when we're going to access this virtual memory. The first is about maybe we are going to traverse all the virtual memory, right? If we are going to traverse all the virtual memory area, then linked list will be a better fit here. And if we're going to search for a specific memory area, then tree base will be a better fit. Your tree can return us like log n time to get the virtual memory out. So even they are kind of storing the same contents, but because they're using different data structure, so they can provide this different functionality. So if the user now is going to traverse, for example, if we are going to traverse, if there is a free virtual memory area that we can use, then we can use a linked list to do the traverse. And then if we are going to identify, if we are going to locate a specific like virtual memory inside this heap area, then we can use this mm-tree1. Then we can quickly get the virtual memory address. Okay. Okay. So maybe you have one question is, so in Linux, how can we access this structure? Actually, at the very beginning of this course, when we are talking about the process, inside the process descriptor, the text dash structure, there is a field called field. So the field will be directly point to this data structure. So when Linux is dealing with the process, it is possible to also control the memory descriptor part. Okay, so this is just I think it's not that quite important, but I think it's quite interesting to let you know. Okay, so what is virtual memory areas? Because we talked a little bit about VMA in the prior two slides. So the virtual memory area, or VMA for short, describes a single memory area over a contiguous interval in a given virtual address space. So I think the key thing is contiguous, just like a contiguous virtual address space, it is called a VMA. So this one is a crop figure from this. So I only crop out the, I think it's not here. I think it's in the bottom of this kind of structure. Actually, part of the structure, there is things called like, okay, here. So MM here, like actually you can get this more data structure if you expand out here, because like this is like the type of the MM is the VM-area structure. And inside this structure, the definition is here. So there are several fields like related to this MM. Okay, so what does those fields mean? The key important thing is here. There are three different fields, the start, and next. So for one memory descriptor, the MM structure, the start field will point to the start for this virtual memory area, okay? And the end will point to the end of this list, okay, like this. So inside the virtual address space, actually you will see things like this. Here, you can use the mmap to point to the VMA start and VMA end to locate one virtual memory area. And this is another virtual memory area. And this is the third one of the virtual memory area. So they should be continuous, okay? So if they're not continuous, they should be in different virtual memory area. Okay, so for each virtual memory area, they are consisted from several pages. So here is one VMA, another VMA, and the third VMA here. And then each VMA, they can be used just like this. Sorry. This. So this heap area, actually, there are several VMAs here. And these text sections, they can be also several VMA. Okay, so VMA just means the smaller granularity for this, like text section, user stack, memory mapping, like this kind of stuff. Okay, so this is for the virtual memory area data structure part. Okay, but I think it is hard to link the text sections and the kind of heap stack with this structure. So I do some example, maybe it can be a little bit helpful. So here is the process virtual address space we already know. There's text section, data section, BSS, heap, like memory mapping, and user stack. Okay. Oh, here's one thing that you know. Actually, in Linux, there's a keyword called anonymous. So anonymous means there is no file packet. Okay. So what does no file packet means? So if you see here is a text section, right? So when we say text section is, there is a code. So the code actually it is stored in the storage device, right? So this is called file packet. Code just like when you write a C program, like a C code, then there is a file. So this is file packet. And data section is because inside your code, actually you do some initialization. So actually this is also file packet. Okay, because you already do the initialization, so we need to store it somewhere. And in Linux, there will be stored inside a file. Okay, but BSS section and heap, actually they are uninitialized, or like they are dynamic kind of parameters. So they are not defined in your code. So there's no place to store this kind of information before you run them. Okay, so those are no file packet. I mean, they are generated in the runtime. Okay. So let's start from the very beginning. Like, in the point of view of one process, actually you will have their text structure. The text structure is going to describe that process. Okay, so inside the text structure, there is a field called MM. So MM can point to the virtual memory structure. So in the virtual memory structure, actually there is an mmap. So, sorry, this one. There is an mmap pointer. So the pointer, sorry, the mmap structure. So inside this structure, there are several fields here. Okay, so let's get started from here. Okay, so actually, for the mmap, there will be point to the first like VMA. So the first VMA there is start and end, right? So this VM-area structure, there are several permissions here. So it is possible to say, hey, this is the read-only sections, and this is also executable, right? Because this code cannot be modified when you are running. So this is read-only. And because this is the binary executable file, so this is VM-executable to say this is an executable like things here. Okay. So there is also some field is about if this is a file packet, then we need to know where the file is. And because this is a executable file, so Linux they'll be put into the /binary/executable, then you can get the executable file. So the C code is put in this, like in this folder and in this position. Okay. So the same things for data sections. Actually, data section they're used for the initialized global variable, because the initialized global variable they're also stored in the code. So and the same thing, there is a start and an end. So even in this example, I draw in the same size. I mean, this one and this one is in the same wide, is in the same kind of size, but actually it depends. I mean, it is possible this section becomes kind of wider, larger. It is also possible. Okay. Okay, so the next one will be the BSS section. So BSS section is going to use for those uninitialized global parameters. So because it is anonymous, so actually we don't have the VM file pointer here. Okay, so there is no file packet. So it means there is no file pack for this one. Okay. And the next one is heaps. So for heaps, actually, it is also another anonymous memory resource because it is created online. Okay, so actually you can see like for from the data section to BSS and heap, they all support read and write. Okay, because they are kind of, you can write the data inside those sections. Okay. And again, because the heap is anonymous, so there is also no file bucket here. Okay. Okay, so like if the heap is not contiguous, because actually these three usually will not be too large because they are all already known before. When the program is running, you will use a compiler to do this kind of optimization. But heap is a little bit hard to do the optimization because heap will be allocated in the runtime. So probably we will get a lot of non-contiguous VMA. And in this case, actually, you can use a chaining to chain all this kind of VMA together. Okay. So the same things like this one is for shared library. So just in our prior example, it would be like our standard C library. Okay, because this is a standard C library, so you can also write it. You can only read the standard library and execute the standard library. So of course, a standard library is file bucket, and the link is usually under the /library/ like this kind of share object here, libc here. Okay. Okay. So the last one will be the user stack. So user stack, because it is going to grow from the top to the bottom. So like here is there will be a flag here to say, hey, this is the growth down like VMA structure. Okay. So actually they are all VMA, but they are used for different function. So it depends on what kind of data you are going to store inside and how the data structure is going to manage them. But basically they are all the same. They are all VMA. Okay. So here are some more details that you need to know for VMAs. Any two VMAs cannot overlap with each other. So actually, if there are some overlap, like you can call the find -VMA to get the nearby VMA, and then to check the end field. So if the end fields overlap with each other, you can merge two VMA together to get one VMA. Okay. And how to create or expand a VMA? Actually, there is a function called do-mf function. Then in this function, you can add an address interval to a process address space, and then expand an existing memory area or creating a new one. So actually, if you still remember, there is a thing called BRK here. Actually, BRK here is going to extend the VMA size. So BRK here, how does it work? Like this. If you use BRK, usually you can adjust the heap size. So I mean, heap will be belonging to, will be back to several VMA region, right? So if we are going to enlarge the heap, you can say you are going to adjust the VM-n here, this one. If the VM-n becomes larger, then the VMA will become also larger. So actually the BRK is going to adjust this VM-n. Okay. Because the start position cannot be changed, but the end position can be changed if there is some virtual memory address there. Okay, so BRK is just going to adjust the VM-n. So usually there's another thing is called mmap. So usually mmap here is going to allocate a new VMA. Okay, so this is the very kind of briefly things that you know. Okay, so this is the do-mf function in Linux. Actually, there are several fields here. The first one is the file. So if there is no file, then it is called anonymous. But if this is a file bucket, just like the data section or like the code sections, then you need to give it the file. Okay, so initial address for finding available space. So there is an address here for finding, and then there is a permission. So permission just like here. This is a read-only or like read-write possible, or like this is the executable. So there are all the permissions. Okay. Okay. So also there's a file offset here. So if there are a file offset for the backup file part. Okay. Okay. So there is another thing is the memory dash user and memory dash count. So we already finished introducing this dash mmap things. So this is a key important things for this MN dash structure that like we're going to manage this virtual memory area, right? So there are two, I think it's quite interesting things to that you know is here is things called mm-users and mm-count. So mm-users means number of threads sharing this data structure. And mm-counts means number of process sharing these data structures. So why they are sharing? So remember when we are going to fork a process, we are using a copy on write, right? So when the process fork another process, at the very beginning, they will share this mm structure. Okay. And for threads, of course they will share because like when a process is going to create several threads, all the threads created by this process, they are using the same structure. Okay. So we need some counter to count about how many threads or how many processes that are using this data structure. Okay. So let me give you a quick example. So in the initialization phase, actually, if process one has 5 threads, so in the MM structure, like the blue part, MM-users will be 5 because of users means how many number of the threads they are related to this MM structures. But because there's only one process called process one here, so the MM-counts will be 1. Okay. So after the first step, the second step is process one is going to fork another process called process two. So at the moment, process one finish forking process two, then what you can see is process one and process two, they all share structure. Okay, they share the same structure. So at this moment, the user part becomes 6, okay, because process two is created. Okay, so as we already mentioned several times in Linux, actually there is no very specific kind of differentiate between process and thread. So actually process and thread in Linux is about how many resources they can be used. So for process, actually they have a lot of isolated resource. They don't really need to share with others. But for threads, they need to share with others. So they are all executable instances. So this is a reason in this example why when process one forks a process, but mm-users still increase 1, right? Because according to the definition, mm-users is number of threads sharing the mm structure, okay? But in this example, mm-users still take 1. So this is the reason, like in Linux, there's not that specific definition between the there is no specific difference between the threads and process. So you can also think about MN-users is just like how many executable instances they are sharing this MN structure. Okay. And MN-counts, of course, will be 2 because there are 2 processes here. Okay. So, I mean, there is one interesting thing is in the prior stage, there's process 1 has 5 threads. So why after doing the fork, we only fork 1 process out? I mean, there is no other threads that are going to be created. Because we say in Linux, when we are doing the fork, actually we'll copy most of the resource like the parents have, and including the threads, right? But according to current multi-threading implementation in Linux, actually we don't do these things. So only the calling thread is duplicated via the copy on write. So probably if this process has 5 threads, and if this process is going to fork a process out, then probably there is only 1 thread that calls the fork, right? So that thread will fork another process out. So there will not be 4 processes or like no 5 threads be copied out. So this is because like Linux doesn't want to deal with the very complex race condition issues. If it really forks five threads out during the forking, then there will be a lot of race condition issues here. Okay, so I think we can stop here and then come back after 10.